So this little section, this little video is on the next couple of sections in Chapter 5, specifically sections 5.3, 5.4, hitting the highlights. Before I did that, though, I wrote a few notes on essentially Emma's question. It seemed, if I understood the question correctly, it seemed somewhat arbitrary how the textbook and my notes were applying constant temperature. So what I wrote here is I said comments on temperature in Chapter 5 in order of appearance. And I hope this clarifies something for you. I think it clarified something for me. So when there's a substitution of what I call the time squared slide, so the definition of changes in entropy. So when you substitute in dq over temperature, T is assumed to be constant. Then it's mentioned that in the definition of Gibbs energy, which is a postulated equation, that T is a state function. What does a state function mean? Well, it means that you only care about the beginning and the end. And at constant T, though, the Gibbs, the postulated equation turns into this. So you'll notice there's no dT term. The assumption is that temperature is constant. So my thinking is it seems that the restriction of constant T here is to aid in the construction of the criterion for spontaneity. And so it was to mimic what was going on earlier in Chapter 4 with the change in the S of the universe. We were kind of paralleling that. And that was really the point of view here, this criterion for spontaneity. So when delta G is less than 0 for a non-reversible process, then you know that that process is spontaneous. These are the conditions in which that is true when T is constant. Similar ideas are going on in that Helmholtz derivation. Also, there's no dT term in there. And you end up getting a criterion for spontaneity for a constant volume process, if you recall. That's how that was generated, and constant temperature. You might also note that the goal on page 178 was to find an expression for determining the amount of work that can be extracted from a spontaneous process if done reversibly. Again, it's kind of narrowing your focus and as a kind of benchmark. And so what I'm saying, kind of an ideal. What's the most amount of work you can get out of a spontaneous process if done reversibly? The value that delta A gives you. In the long Gibbs energy derivation on the fundamental equation section, I think the goal there was to generate general expressions for how different variables affect delta G. Now, it was done through differentials, and they prescribed this analysis only for when expansion work occurs. So you could see that there is a relationship with pressure and temperature with Gibbs energy. Also, in this derivation, they went on to calculate an expression for delta G. That was the maximum non-expansion work you can get from a reversible process at constant T and P. So earlier we were talking about the most amount of work you can get out of a spontaneous process if done reversibly, just in general, the maximum work possible. Here, it's specifically the maximum non-expansion work. I think my overall answer to the question about enforcing constant temperature or not is what the goal is, what information you're trying to extract out. And it seems like sometimes they do allow for temperature to change, sometimes they require it to be constant. So let's see where we can go with some information in 5.3 and 5.4. So 5.3 is all about standard molar Gibbs energies of formation. So look at that here. We have standard molar Gibbs energy of formation. There's really 4 pieces here. You know what? I forgot to write in a bar. That's where the molar comes in. So just like enthalpy, we cannot measure an absolute value of Gibbs energy. You can't stick a meter on a chemical reaction and get a G. Therefore, we're going to calculate delta G's of reactions using up a convenient standard of setting standard states of elements in their most stable allotropic form at 1 bar and 298 K as the standard states of those elements. And then we could use values of the formation reactions for those elements, or compounds, I should say, formation reactions of compounds from their elements to get numerical values. So there's a couple of different ways. This is about as simple as reaction as you can get. You have a mole of graphite combusting to give CO2. You can get the delta G of that reaction a variety of ways. You could look up delta G's of formation of the components in an appendix. Usually those lists are not as comprehensive, though, as delta H values and delta S values. Or really, I should say, in particular, you get delta H from delta H of formation values. That's what you look up in the appendix, and you look up absolute entropies in the appendix. But you need to manipulate them, products minus reactants, to get the values. We will also see that delta G's of reactions can be obtained from equilibrium measurements, that's equilibrium constant measurements that we'll do later, or electrochemistry, which unfortunately we won't get to this semester. Calculations in your text demonstrate that the combustion of glucose and the combustion of methane are quite exergonic. I just wanted to say exergonic out loud to make sure I pronounced it correctly. These are pretty negative values, so these are very spontaneous. The combustion of glucose, the combustion of methane is spontaneous. But if these combustions are so favorable from a free energy point of view, why are they indefinitely stable? You could have methane in a tank and it could sit there for years and years and years, or even expose it out to the environment, and it's not going to explode. Always remember that talking about spontaneity says nothing about kinetics. It says nothing about clearing an activation energy barrier or the fact that the molecules can't come in contact for some reason. So kinetics and thermodynamics are kind of always at odds with each other. I noticed an interesting footnote on page 184 that says when there's no change in delta N of gas molecules, delta U and delta H is equivalent to each other, and delta A and delta G is equivalent to each other. So that's an interesting tidbit to keep. So in the next section, we talk about the dependence of Gibbs energy on changing temperature or changing pressure. Now, because Gibbs energy is so central to thermodynamics, we need to explore its properties. Now, there's a set of these 4 fundamental equations here. 2 of them were derived in our book, and 2 of them were derived in the appendix, 5.1. You could see that they have similar forms, but you have to be careful you're writing things in the correct order and with the correct sign. So, how about the dependence of, what are we going to do here? Temperature. So, take equation 510 and apply constant pressure. So, therefore, we simplify the equation to this. You could rewrite it as a partial derivative to show that the partial of G with respect to T is minus the entropy. That's interesting. Recall that the definition, the postulated definition of Gibbs free energy is H minus T times S. So therefore, I could rewrite the postulated form of Gibbs energy as H plus T times the partial. Gibbs energy thus goes down as temperature is increased because absolute entropies are always positive. Did I get that right? Right, now that I see it. So since absolute entropies are always positive, this partial derivative, whoops, why isn't that working? Oh, my pencil runs out of juice at an inopportune time. So I let those electrons flow into the pencil, and that usually is enough. So this, since that term is negative, Gibbs energy always goes down as you increase temperature because absolute entropies are always positive. If you divide the expression by T squared and rearrange, you can get this expression here, and then reorder it, and you get that one there. So why do I want to have those negatives? Well, on the right-hand side, this 2-term expression is the partial derivative of G over T with respect to T at constant P. Rewriting it that way, this version is called the Gibbs-Helmholtz equation when applied to a finite process. Again, so it's relating changes in Gibbs free energy with respect to temperature. How the partial derivative changes with respect to temperature is equal to this expression. What does that allow us to do? Gibbs-Helmholtz is useful because it will help us know the position of equilibrium and perhaps guide us how to change conditions to shift equilibria. You might remember in general chemistry that adding heat or removing heat can shift the relative amounts of reactants and products. I know that we have a experiment in the 102, and I don't know if you do it in 102, where we set up a bunch of different equilibria and we add a stress to the equilibrium and make observations. So you could change which direction equilibrium lies by changing these conditions like temperature or pressure. The dependence of Gibbs energy on pressure at constant T is expressed here. I'm doing exactly the same thing. You eliminate the second term from the fundamental equation, rearrange it into a partial. This is saying that Gibbs energy always increases when you increase the pressure from P1 to P2. As an example, for an ideal gas, you can plug in the expression for an ideal gas into here, do the integral, and if we set P1 to 1 bar, the quote standard state, you can end up getting this expression 5.18 when eventually expressed in molar quantities. 5.18 relates the molar Gibbs energy of an ideal gas to its pressure. Later, we will see a similar relation relating Gibbs molar energy to its concentration. What this is saying is that if you know the Gibbs energy in its standard state, 1 bar, adjusting the pressure essentially adds a correction term. Read the last part of 5.4 to consider condensed phases. Essentially there, you're not having a great effect on the Gibbs energy if you change the pressure on a solid or a liquid. Maybe if you're doing some calculation of geological changes when pressures are so large, but I think there may be an end of chapter question that relates to that. A couple problems to think about. These are completely random. I thought they were related though. Proteins that are functioning are native. Denaturing unwinds them I know everyone's had some biochemistry by now, and renders them non-functional. If delta H for a denaturation is 512 kilojoules per mole and delta S is 1.6 kilojoules per mole, comment on these signs and calculate the temperature when denaturation becomes spontaneous. Delta H is expected to be positive, endothermic, because many hydrogen bonds and intermolecular forces must be broken to break apart the protein. Not break it apart, but to unwind it. However, some energy is retained, quote, given that the number of water-protein interactions will increase. In other words, you can't exactly say that entire 512 kilojoules is going straight into breaking bonds, because there will be an increased number of interactions with water. However, as a net, if a typical hydrogen bond is in the 10 to 15 kilojoules per mole range, then there's a net of about 40 equivalent H bonds that are broken in the denaturation. The delta S is positive. That's expected to be positive given the less ordered state of a denatured protein flopping around. Let's write the molar entropy of argon as a polynomial. Shouldn't surprise you. As you warm something up, you're going to basically allow more energy to be stored by the system. Although for argon, I'm thinking now, I guess that's just you're assuming constant pressure. You're activating more microstates. You're not activating other modes of energy storage. But in terms of disorder, you should expect that to increase at increasing temperature. Calculate delta G naught when, my naught's in the wrong place, where 1 mole of argon is heated at constant pressure from 20 to 60. So use this re-expression of the integral. So we're going to use our partial expression we had earlier, rearrange it, take the integral of both sides. We get a number minus 6240. So we expect the Gibbs energy, to drop when we increase the temperature, which is something that we said earlier. Calculate delta A and delta G for vaporizing 2 moles of water at 100 degrees. The molar volume of liquid water is 0.0188 liters per mole. Put that dot in there. The delta G is 0 because when you're doing a phase change, that's considered to be an equilibrium process. So delta G is 0 and an equilibrium process. Delta A, on the other hand, is delta U minus T delta S. Delta U, using the first law, can be replaced with Q plus W. The Q is going to cancel the T delta S term, since we're doing a phase change, reversible again. So the delta A is basically equal to the work. And so for an expansion, essentially we have an expansion against 1 atmosphere of pressure. We're looking at delta V, the volume of the gas minus the volume of the liquid. I did the ideal gas law here. I subtracted the volume of the liquid with the given information, and I ended up, in a strange coincidence, getting an almost identical value that we had earlier of 62, around 6,200. Let me double check. Does that make sense that that's positive? And suddenly it's late in the day. My mind is numb. It is positive. So it's doing work. You're doing work. Hold it. Wait now. Delta A, if it's doing work, you would be losing energy. Yeah, I think a minus sign disappeared here, folks. And again, I'm out of juice. But let's see. I think that's a minus. So that's just a coincidence that number 37 and 40 were basically rough equivalents of each other. All right. Try to work through these sections. Please ask any questions, and I will see you on Wednesday. Bye-bye.